All right, so we're going to understand what the pKa means about a buffer. And remember, a buffer is a weak acid and its conjugate base, or a weak base and its conjugate acid, and a mixture in a beaker. All right, And we saw that when I mixed acetic acid and its conjugate base, acetate ion, sodium acetate. I mean, it could be any salt of acetate. And I put them together in a beaker. I got the we saw that we got a pH in between my pure weak acid and its conjugate base. pH was somewhere in between, and we're going to say, hey, what does this mean? Okay, so a buffer is a weak acid, its conjugate base. Now, weak acids have values that describe their ionization. That's the Ka value, all right? And the Ka value you can turn into your pKa value if you take the negative log of it, all right? And then the interesting thing comes about when I take a 50% mixture of these two. All right, I got a 50% mix. My pH will be equal to my pKa. All right. Now, remember, this is also in a titration, the half equivalence point of in this case, a weak acid with a conjugate base. All right. So this is how they're related. The pH of a 50% mixture is basically your pKa value for your weak acid. Now, the reverse is true of a weak acid a buffer where you've got a weak base and its conjugate acid, where I'm going to have a Kb value for my weak base. All right. Now, this Kb value, I can take the pKb of it, take the negative log of my Kb. If I make a 50% mixture, here my pKb is going to be equal to my pOH. All right. And this is at the half equivalence point. Now it's there on a titration curve. All right, that point there when it flattens out. And then I can with this equation, I can relate my pKb to pH, because pOH plus pH is 14. So then I substitute pKb for pOH, and I'm going to get pH. All right. Now that we understand where the value comes from, the next thing is, what does the value do for us? The pKa for a weak acid is a 50% mixture of it and its conjugate base, all right? And vice versa for a weak base. It gives us power over that buffer solution and allows us to use that value to orient ourselves with the buffer, and I'll explain right now. So, buffer's got a pKa. I want you to think of it like an orientation thing, something you use to orient yourself. With a buffer, you can orient yourself by your pKa value, because if your pH is less than your pKa, what that means is you've got more weak acid than your conjugate base. All right? I've got more weak acid than my conjugate base. All right? On the flip side, if it's greater than, my pH is greater than my pKa, I means I have more conjugate base than my weak acid. Now, for a buffer where the weak base and its conjugate acid, it's the same thing, but in terms of OH concentration, where if my pKb is greater than my pH is greater than, that means I've got more base than my conjugate acid. All right? And if it's less than, it's the opposite. All right? All right, let's put this into practice with some solutions. All right, got some solutions that I've made, and then let's use this to figure out stuff about this acetic acid acetate solution. Okay, so here I've got a mixture of acetic acid and its buffer, acetate ion, and you can see that the meter there is about 4.7. That's less than the 4.8 that we measured, or that's less than its pKa value. Its pKa value, I think, is like 4.8. So that means we just have more weak acid than we do conjugate base. I have got, um, 60-40, something like that. I've got more of the weak acid in there than I do the conjugate base. So that's why it's like an orientation thing. I know the pKa value is the 50-50 mark. All right. And then I can use that to be like, all right, I've got more acid or more base in it. All right, let's do another one. Here's a different solution. All right. Here's a different solution. And you can see now my reading is above my pKa. Therefore, that tells me, hey, I've got more conjugate base in this solution than I have weak acid. All right. And uh, because my pH is above my pKa. All right. And that's how they're related and how it's useful.